this is a typical analysis we can repeat in the future for what we call semi-discretized PDEs. So we discretizing. Why do we call it semi-discretized? Because we are discretizing only the spatial derivatives, right? So all of these analyses are for this differential equation. dwi dt equal to wi plus 1 plus wi minus 1 minus 2wi over delta x. So this is called the semi-discretized, right, equations. Because we are discretizing the spatial dimension, we got rid of the spatial derivatives, but we didn't get rid of the time derivative. Okay, and for us to be able to know how the numerical error accumulate, we often have to look at the fully discretized differential equations, which means we also want to discretize time. So let's also just use an example to look at this. Let's use forward-Euler, the simplest discretization scheme, to discretize this equation. And if we use forward-Euler, what we get is wi. Now we use a superscript to denote time step. Okay, this would be equal to wi plus 1, also n. In forward-Euler, we compute the time derivative using at step n, and use the time derivative at step n to get to step n plus 1, fully discretized. Okay. So for the fully discretized equation, we can do exactly the same analysis. We can perform the same analysis. The same analysis is going to give us not just the time derivative, but actually what the solution at the next time step look like. It's going to give us, let's just use this slide. So it's going to give us win plus 1 minus win over delta x, or delta t. Is going to equal, for the same type of solutions, analytical, for the same type of sinusoidal functions. Okay, so if the solution is sinusoidal, it's going to be equal to what we derived to be win times this cosine function, right? Cosine of 2 pi k delta x minus 1 times 2 over delta x squared, right? So that's kind of the proportionality constant we get in deriving the exponential. But instead of being equal to the time derivative, we are equal to an approximate time derivative coming out of the forward-Euler. The result is that if you put all the known values on one side and the unknown values on the other side, which means the only unknown here is this term, right? Okay, the only unknown is the one at time step n plus 1. What we get is this is equal to wi at n plus delta t. Well, let's move this together. Delta t times 2 over delta x squared cosine 2 pi k delta x minus 1 times win. Or it's equal to win times 1 constant. And that constant is the important thing that is the result of our stability analysis. For the solution to be stable, what should this constant be? Or what values can this constant take if I don't want the solution to be blowing up? Pardon? Less than 0? Less than 1, yes. But also, it has to be greater than minus 1. Right? So if this constant is minus 2, then I get minus 2 at the next step, plus 4 and minus 8 plus 16 minus 32, etc. I'm going to blow up. So this constant has to be within minus 1 and 1. Okay? It's trivial to have this satisfying the upper bound, because the cosine minus 1 is always less than 0, less or equal to 0. But it's actually non-trivial to satisfy the other condition, that it's greater than minus 1, because 1 plus 2 delta x, 2 delta t over delta x, cosine 2 pi k delta x minus 1 less than minus 1 means that greater than minus 1 means that if I remove this, it has to be greater than minus 2, right? Which means if I remove the 2, it has to be greater than minus 1. Okay? And remember, this k can be anything. If I start with an arbitrary initial condition, it probably contains Fourier frequencies. I mean, if you do Fourier series analysis to it, it probably contains a lot of different k's. It's a summation, it's a weighted average of many frequencies. And if only one of these frequencies gets unstable, that frequency is going to be amplified indefinitely. And the whole solution is going to blow up. So the condition does not have to be satisfied for one particular k, it has to be satisfied for all possible k's. And for this to be satisfied for all possible k's, okay, my delta t over delta x squared has to be what? Has to be not too large, right? Because this actually can go into the range of minus 2 to 0, right? So that's the range of a cosine minus 1. I mean, that's the range of the function cosine minus 1. If you plot the function as a function of k delta x, I mean, cosine minus 1 can be as low as minus 1 or minus 2. So for this whole thing to be always greater than minus 1 for whatever k, I need what condition? I need this to be less than what? Less than half, yeah. So that's the condition, that's the stability criterion. For the heat equation, yes? Oh yes, I have a 2. I originally have a 2. I originally also have a plus 1 on the left hand side. When I move the plus 1 to the right hand side, I have greater than minus 2, and I drop the 2 on both sides. Yeah, thanks. Okay.